right, in the last hour, we came to log linear models. Before that we came to log linear models. Right, in the log linear models, well, what we are trying to do is we are trying to predict the expected counts in contingent tables. Right, in the contingent table we have observed counts. Right, for example, maybe right maybe the one example we can take, maybe somewhat related to what I was thinking about, was the malformation of babies. Right, maybe different levels of alcohol, so that is X, and Y maybe the baby is malformed or not, 0 or 1. So those are contingent tables, and we have the number of observed counts for each category, and these are what we call NIJs, right? N11, N12, and so on, N21, N22, and we want to predict those counts, and the expected count we write in log linear models. We can express the log counts, and then we can predict the counts using a model like this, depending on our assumptions, and we were looking at various assumptions. So it depends on the probability of membership in each cell, and that probability of membership can be expressed in different forms. Now, if they are independent, that can be written as the pi I plus times pi plus j, and as it gets bigger and bigger, they're not just two-dimensional. When it gets higher, this gets there are various options. So we were talking about that. So the idea there is to predict the expected count using these categories. So when you know one cell is in which category, and we want to be able to predict what the count might be, and that's what we're talking about. And we were working with the two-way tables, and last time we came to three-way tables, and that is what we were talking about. We came to this, and in that we have three variables. So this is a table. So this may be X, this may be Y, and then a third variable. So we have layers, and we have cells. So in each cell we have the number of individuals falling into that cell, and we want to be able to predict based on which X level, which Y level, and which Z level that cell is in. And for that, it depends on the probabilities. The probability of membership in that cell, IJK cell, and we may have lots of assumptions, lots of different assumptions on this. One of them is we were talking about these various notions of independence. One of them is mutual independence, where it is equal to the marginal probability of X, marginal probability for Y, and marginal probability for Z. And in that case, we saw that the model can be written this way, and the first one being when you take the log of this, the first one being this one, and this is what we denoted by lambda x for X variable, the ith category, and the effect of the Y variable, the jth category, and so on. And that is the mutual independence, or sometimes we call it complete independence. And we did say that we write it like this, X, Y, Z, all separately. And other things that we can think about, the joint independence. Now, Z is jointly independent of the other two, means In probability, we think of these two as one variable. So this one and this are independent. So it is ijk. So ij is one category. This, so you can write this as a product of ij, the marginal distribution for I and j together, and the marginal distribution for z. You can do that, and we should be able to do that for all ijk. And in that case, the model turns out to be this. Right? So x, right, xy independent of z. So you see that one xy term, and that's the model. And we write it like this, right? Xy and z. Right? The z is jointly independent of x and y. And the next is conditional independence. Right? Conditional independence means the conditionally, the probability of yj given any category, any level of z, we should be able to write it as this is the definition. We should be able to write it as, right, the conditional, marginal conditional probability for I, conditional again on the same condition, and the marginal conditional probability for j, for y equals j at the same level of k, right? We saw that, and we can write this as writing down the definition of conditional probability, that is pi ijk divided by this and this divided by the probability for this one only, that is pi plus k. You can use write that one that way. You can write this one this way, this divided by this and this. That means this one divided by this one, that is pi plus k, and this one is this one, and this one is this one, right, plus jk divided by the marginal distribution, marginal for this one. And then with the cancellation on this side, we have pi on this side, it turns out to be just this. And we have two of them, but one of them on that side as well. And now if you take, if you multiply by n and take log, when you multiply by n, you get mu, and then if you take log, you get this, right? You get this, where this one is the log of n, and you can identify them as the log of some phi. And so that is the conditional independence. So I look at this carefully, and when you have these two, that is the conditional independence model, right? X and y conditionally independent given Z model, right? So Z repeats, and you write it like this: X Z, Y Z. So if I talk about this model, X Z, Y Z model, you should know that means the condition, right? X Y conditionally independent given Z model, which means this model, right? And then we were talking about homogeneous association model. Homogeneous association means any pair is independent given the other one, right? So we have this. So you see that this means right, those two, right, tell you that Y is independent given X, because X is repeating. And if you look at these two, you see that X is independent given Y, because Y repeating, and these two X, right, XY independent is conditionally independent given Z. So that's what you call, right, homogeneous association. That means each variable, right, any two variables are conditionally independent given the other. We write like this, right? You see that each variable is in two of them. And then we were talking about, I just mentioned this, when we talk about, right, this kind of thing, these are odds ratios, right? You know the odds ratios are for 2 by 2, right? These two values, the mu 1 1, mu 2 2, mu 1 2, mu 2 1. You multiply these two and divide by those two, and when you have too many, right, many cells, you can take any one and compare with anyone else, and that's what we do. So the idea of the odds ratios, and that if you take log of this, you can write like this. So the log of these two minus log of these two, which means, and these can be written in terms of lambdas. Each log mu ij can be written in terms of lambdas, and that turns out to be this for this model, right? So it is kind of easy to remember because it is lambda for 2 by 2. So this log odds is equal to lambda 1 1 and lambda 2 2 minus lambda 1 2 and lambda 2 2 for xy, right? So it's kind of a familiar form. It is not multiplying. This time you subtract. So that's there. And the important things to note is that we notice that it's independent of the condition, which is what we expected, right? The conditional independent means right, x and y are independent at every layer of k. So that is what this means. And well, we did say that this can be written in the usual log form, right? With any variable, but with dummy variables, right? With indicator variables, and we were looking at the full model. The full model is a model with all those, right? X, Y, Z, and their products, and the three interaction. And if you try that one, the number of parameters is going to be I, J, K. That means the number of cells available, which means that is the saturated model. Right? We denote it like this, and that's where we stopped at. And I want to have a look at this example. Right? In this example, some comments on R, and when you write X, this colon Y, that means we are telling R just use that interaction. Right? Just use that interaction. And if you put X star Y, that is equal to use XY and X and Y. Right? So star means that. So when you read quotes, you should know that. And this means in R, if you say X plus Y square, that means the model XY, you want XY terms and YZ terms and XZ terms. All terms, not three-way interactions. And you will have XYZ as well, right? Because then you won't have this one. So this means that, right? When you write in R commands, when you write this one, that means that model. That means the homogeneous association model, right? So this is homogeneous association model, and right. So right, and the others. For this one, for example, that's the homogeneous, right, association model, and you can write this way: X, Y, Z, X, Y, Y, Z, sorry, X, Y, X, Z, and Y, Z. Or you can write like this. And I told that this one, when you write this one, it's going to anyways add these. Right? X and Y will be added, this X and Z, Y and Z. So when you have X twice, that means X. Right? So these two should give you the same output. And if you write this one, that should give you exactly the same output as well. Right? So this is also the homogeneous model. So there are lots of ways to write the same, right? And you should get exactly the same output in R for those three. And that's right. We will have a quick look at that one. And well, and after that that's the end of these lectures. This one is right in this study. What they are doing is they are studying the association between these three variables, right? Among these high school seniors, right? There are these habits: alcohol, smoking, cigarette, and smoking, and use marijuana. So they have this. So this is a three-way table, three variables. Alcohol is one, cigarette is one, marijuana is one. Right? For each level of alcohol, we have two tables. So this is the table, right? For for cigarette and marijuana, and these are for alcohol equals yes, and for alcohol, the other category, maybe if you call this K equals 1, this K equals 2 category, and we have another table. So we have that, and now we're going to analyze using what we were talking about. And I first read them, and here's my data I created. So I put the data right in the data, right, this format, in the data frame format. So this is right, one variable, this marijuana yes, and right, cigarette yes, and alcohol yes. And for that there were 11 people here. Yes. And then yes, no, we had this many people. So I wanted to put it that way. And now right, you can compare these two. And now we can ask R, and we want to predict these counts using these three variables. Right? So here are some of the, right, this one. And if you see this, I expect you to be able to tell me that this is that homogeneous association model, right, in the exam. Right, you expect you to understand, because I told you that this means that, right, x plus y plus z to the power 2 means this is equal to AC, AM, and MC. Right, so this is the same as that. So you should see that. When you square, you get something like that, right? And the others are there too, AC and M. So they are coming anyways. Whenever you see AC, then A is there, C is there, and AC is there, right? You need to have those two. So that gives you that. And if you want to see what it gives you, here it is. Right? Here it is, and as an exercise, and I suggest you to try to identify the lambdas. Where is lambdas from this? Right? Shouldn't be very difficult, right? And you should also see some of them. Now you see that for A, alcohol, right? There is one. Alcohol yes. That means alcohol has two levels, yes and no. It has taken no as the reference. And for cigarette also yes no, and it has taken no as a reference. And these are there. So they are, right, the products of these, the products of those. And so that is this model, the homogeneous association model. And if you ask this one, it will only have these two, right? And these will be there. Right, here it is. So these will be there, and it will have these two. So you don't have MC, right? You don't have MC like we had before. And I call this fit 2. So this fit 1, I call this one fit 1. And this one I call it fit 2. And fit 2 is this one. And I tried this one. And if you try this one, you get exactly the same thing as before, the previous one. Because now in the previous one, I typed in these. You don't have to do that. When you type AM and CM, it's going to add the low order terms anyways. So I asked for this. And you see that they are the same, right? So you should know that. So that they will, right, R will put automatically the low order terms. So you don't have to do this. So if I want this model, it is not necessary to, if I want this model, it's not necessary to put this part. If you do that, it's fine, but you don't need it. Right? And now, when you have the model, you can use the model to predict, and that's the point, right? That's the idea. The idea is in the table, we want to be able to predict now. If you have a high school senior, you can ask the question, right? You can ask those questions, and you should be able to count if I give you, okay, how many people like this, right? They use alcohol and cigarette, right? They use alcohol yes, cigarette yes, and marijuana yes. How many people like that? right, in that entire sample. So if I give you the sample, so we should be able to do that. So we can predict that, right? When you have the model, we can predict what this number should be, and that's what I'm trying to do now. Right? You can predict. Here's how we predict. Right? You can say predict using whatever the model you want. The first one was the homogeneous association model, right? And using that one, predict response. Response means, you know, the model is for log mu. Log mu is equal to lambda plus other lambdas. If you want this one instead of log, you have to say predict equals response, and then it will give you the actual mu's. And I call it mu hats using model 1. And the other one is using this model. Right? This model. From this model, it is not the homogeneous association, right? One of them is missing, right? This AM is not there. AM is not there. So this model. In other words, I'm trying to see if AM is necessary. And if you want to do that, you can try that model. And now you can calculate the predicted values, and I did. And if you want, you can put them in a table like this: the actual data table, and to that. And I'm writing down the predicted counts using this model, and predicted counts using this model. And here I did it. And now this is the actual data. This is the actual data. This is predicted counts using homogeneous association model. And this is the predicted data using the second model. The second model, I did not have AM, right? So without this, the others were there, right? Cigarette and alcohol, and cigarette and marijuana, but and this one was not there. So, right, it is using this model. You only have these two, right? And here are my predictions, and now we can compare and see which one is, are they okay? Is this okay, or is this one okay? And these are the actual counts. You can compare the actual counts, and with this model, it is 9, 10, right? Not too different. And this is 909. It is also close enough. And this is the actual for this one, for this category, and this is the predicted using this model. They're close enough. And this one is a bit off. It's 438, whereas this is 538. Right, so that means this model doesn't appear to be predicting that well. And you can go through that and comment, right? And I would say that now, if you, for some of them, if you look at this one, and this one, and this one, they're close enough, and this one is not. So I would say that this one is probably is not doing a good job at predicting the actual counts. So that gives you the idea that maybe this is probably not very good. Maybe this one is okay. So homogeneous association is okay, appears to be okay. This one does not appear to be okay because the predicted values are not that close to the actual values. And right, and now, well, a couple of other comments. Right, and I did make that comment last time too, but this maybe for the second time. Now, if you look at here are the counts. If you look at well, this any model, I'll take this model. Now that is the model. That is the model in which, what is that model? Model 2. In the model 2, model 2, this M is repeating. C is there. So that means A and C independent given marijuana. Right? So that's the model, conditional independent, A and C conditional independent given marijuana. That means for any level of marijuana, you can make two tables, A and C tables. For marijuana level, no, marijuana no, and marijuana yes, another table like this. And at any given level, A and C independent means when you calculate the odds ratios, independent means the odds ratio is 1. So for these two tables, the odds ratios must be 1 regardless of what the level of M is. And we can check if that's the case. Now I did that. So I took marijuana equals yes, and then write the AC, right? AC, right? AC and say cigarette yes, no, and alcohol yes, no. And calculate the odds ratio for this table, maybe for one of them, marijuana equals yes. And you can calculate the odds ratio, the expected odds ratio. So you can calculate this one times this divided by this times this. So this one means the count, the expected count for marijuana equals y, and cigarette equals y, alcohol equals y. That means this. So this is the expected count if you are using this model. And I pick that one here. And this one is cigarette is no, alcohol no, marijuana yes. So marijuana yes, cigarette no, alcohol no, this one. And for that one, here's the predicted value. So that this one is that. And I use that one there. And then divided by this times this, right? And this one is marijuana is y, cigarette no, alcohol yes. So we have to find that one. Marijuana yes, cigarette no, and this one. Right? No. Yeah, that one is this. Right? So marijuana yes, cigarette no, and this one is white. And I picked that one, 45. So that is this one. And the other one, the other one is this one is marijuana is y, and cigarette y, and alcohol no. So marijuana is y, cigarette y, and alcohol no. So that means this one. So I put that one in here. And if you calculate that, that should be exactly equal to 1. You can use your calculator and check that's equal to 1. So that is for marijuana equals yes. And similarly, you can redo the same calculations for marijuana equals no. Just like I did, identify these categories, marijuana equals no, and identify for that table, right, the cigarette and alcohol. Maybe yes, no, alcohol, yes, no, and figure out those values. And if you do that, that should be not just approximately, that should be exactly equal to 1. Right? So, and as we expected, and that's what we call the model of what the cigarette and alcohol being independent, conditionally independent given right, marijuana. So we expected that, and so these counts are calculated assuming that. So we should have that one. Right? Is that clear? And now, if you want to test, now these are important. Now I can ask you, right, test the model, compare the model AC, AM, CM model, compare this model, right, compare this model with, right, compare this model with the other model that we calculated, right, AM, CM model, AM, CM model. First you should understand what this means. Right, AC, AM, CM model. You should know what that means. That refers to the first model, the fit one that you were talking about, these kind of mutations. And this refers to the model in which A and C are conditionally independent given marijuana. And we have those two models. We just call them fit one, fit two. Fit one is this one, and fit two was this one. Right? And if you want to do that, if you want to test, what you should do is you calculate the G squared for that test. You can use the likelihood ratio test. This is the likelihood ratio test. So likelihood ratio test is so this one is in this one is a part of that. So we calculate the G squared, the residual deviance for the smaller minus the residual deviance for the full model. And the smaller model will have bigger residual deviance. And we have that in our outputs. Right? Now this is the reduced model, and here is the G square. Right? And the full model is the model with all of them. Right? So remember, this is the full model, the homogeneous association model, and for that the G squared is 0.337. So remember, that's 0.37, and you can just subtract those two, and that is the G squared. That's the likelihood ratio, right? Test statistic for testing the null hypothesis that whether you can drop this term from this model. So we can calculate that, and we saw these numbers. And if you saw the degrees of freedom, they were there right there, and this one had degrees of freedom too, and this and the full model had degrees of freedom this. So the difference has degrees of freedom this. And now you compare that with this one. So this one, so you compare that with the chi-squared one, right? Chi-squared one is 3.84. So if this is bigger than the chi-squared, that chi-squared one, alpha equals 0.05, which is this one. We can remember, we saw that multiple times, and then you reject. That means, no, you cannot drop that, right? So you cannot drop that, right? And that's how we saw. That's how we saw in here too. In our calculations, we saw that this one, when you drop, these are very different from the actual values, and these are close enough. And if you drop that one, right, you expected counts are not going to be anywhere near. Now, for example, this one 538, this one is 438. So it's a big difference, 100, right? So we were able to see that by looking at the predicted values, and our test is saying that too, right? And well, that's almost right the end of it. But a couple of things you can do that using R. We have seen that before. You can ask R, give me the ANOVA command, right? ANOVA, compare these two, and you have to say test equals LRT, or if you want Pearson, you can say test equals Pearson, one of them, right? LRT is the likelihood ratio test, and that will give you this, and it tells you that it's going to pull out those residual deviances, and it's going to find out the key information, and we saw that we had to go to the original model to figure out those things. And then it's going to calculate the difference between these two. Here it is, and we calculate them manually. Here it is, we calculate them manually. And then you can compare that with the chi-squared table value, which is what you would do in the exam. That is 3.84. That's chi-squared 1 with 0.05. If you have this one, this says the p-value is this. That means 2.2 times 10 to the power minus 16, which means 0, lots of zeros. And 2, and that's way below 0.05, so you reject. You can see that as well. This one is way bigger than this, and the same thing is there with this one, right? It's not just a little bit less than 0.05, much less. So that's one comment, and that's pretty much everything. And one last comment, and we're done. The last comment is there's a connection between logits and log linear models. Right, I want to talk a little bit more about that, but I thought maybe I'll stop here. You can actually connect this to logistic regression. You can connect this to logistic regression. Now, in logistic regression, we predict logits. Right? Logit means, well, I think it's better to keep this one in mind. The I cross 2 tables that we were talking about. The best example that we were talking about was the malformation of babies, depending on the mother's drinking category. Right, mother drinks various levels of drinking, maybe a little bit and maybe more, lot more, and so on. Those drinking categories, and the baby malformed or not. Right, the baby malformed, yes or no. So that is that's what we call an I cross 2. There are I levels here, and 2 on the side. And in that one, if you can remember, when we were looking at the logistic regression, in logistic regression, what we tried to do was this: predict log, log of the baby being malformed, that means for any level, for maybe I may be the mother's drinking level, maybe a little bit, or maybe I equals 2, maybe moderate, and I equals 3, maybe lots of drinking. And so based on that, we want to be able to predict the probability that the baby will be malformed, right? And for that, what we calculate was this, right? In logistic regression, we use this, right? The pi, depending on this, the probability that the baby will be in this category instead of, right, 1 minus that same number. Right, these are the odds, the log odds. And we want to predict that one. Right, we came up with the models. Now, from this also you can do that. Now we can think of this as a contingence table, because they're counts. These numbers are counts. How many people were there, how many babies were there in this category, and how many babies were there. So that is just a special case of the contingence tables, for which we can use this, right, the log linear models. Now I can give you a question on log linear, right, the data analysis. I will give you the data analysis using log linear, right, models, and I can ask you to predict these kind of things that you would normally predict using logistic regression. So the output is not logistic regression. The output is based on maybe, right, this one, the log linear models. You can do that. So how do you do that? Now, if you want to calculate the log odds of a baby being malformed, when the mother's drinking habit is this level, little bit. So I may be any one of them, and that is, that's equal to this 1 minus I means the probability of this one, right? So this one is this is pi I1. When the mother's drinking level is that, 1 is baby being malformed, and this is maybe y, this no is 2, right? So this the second column. So this one is the probability for the second column. This is the probability for the first column. We can multiply the top and the bottom by anything we want. We can multiply it by n. And if you do that, n times the probability for any cell is the expected mu. Right? N times the probability for any cell is the expected mu. So this one is the expected number of babies malformed. 1 means malformed, right, if the mother's drinking level is that, divided by, this is the expected number of babies not malformed for the same level of drinking, right? And that can be written as this, right? That can be written as this. And these things can be written in terms of lambdas, lambda plus lambda xi plus lambda y2. So log mu ij's, ij even k's, those can be expressed in terms of lambdas, and the lambdas will be found in your log linear output. Right? All lambdas are there in the log linear output, and you know how to find out the lambdas. So you can actually calculate whatever you right, most of these probabilities that you calculated using log linear models, using the logistic regression models, using these models too. Right? So that's the comment, and so we have lots of connections, and right, combining those two, but I didn't want to go through that much, but this will give you the idea. Right, and that's all what we have. And I'll post this one, and you don't have to take it. I know that I just added this one, these last two slides. Any questions on that?